This video is for section 9.5 in your notes, which in your chapter 9 book will be section 9.6 because we skipped a section. There'll be two videos. In the first one, we're going to talk about what a power series is and look at radius of convergence. And then in the second video, we'll look at the ratio test. So you can take a look at your learning objectives. Let's just get right into what a power series is. You'll also notice in this video there's spots where I've taken notes already, so you might want to pause the video and put those notes in your notes. So it says in section 9.3, we introduce the concept of approximating functions by Taylor polynomials. For instance, we spent a bunch of time looking at approximating the function e to the x with a Maclaurin. Remember, Maclaurins are centered at 0. With a Maclaurin polynomial, and here is a third degree approximation for e to the x. So this would be a third degree polynomial. In that section, we saw that the higher the degree you use, the better the approximation becomes. Starting in this section, we see that several types of functions, including e to the x, can be represented exactly. So now they're not really calling it approximation. They're saying exactly by representing the polynomial as a series, a Taylor series. So for example, if you take your polynomial up here and you say, hey, I'm going to go forever, which means I'm going to have an infinite number of terms in my polynomial, then it's going to be exactly the same as e to the x. So that's pretty powerful. Here's your definition. So it says for each real number x, it can be shown that the infinite series on the right over here, so that's your polynomial, your Maclaurin polynomial, or now we're calling it a Taylor series, converges to e to the x. So it is the same. By doing this, however, some preliminary results dealing with the power series will be discussed, beginning with the next definition. So this is your definition of a power series. This one's a little light in my copy, but it says that if x is a variable, then the infinite series of the form, so this is like a coefficient, and x to the n would be x squared, x to the second, x to the third. So you can think of this as representing your polynomials as a series, is called a power series. So this one would be centered at 0, and then this one would be centered at a c value. And then just a reminder, you can start at another n value than 0. You could start at any integer. And then here, n is your exponent. So this would be centered at a number. This would be your first derivative, and you would have an exponent of 1 here. So that would be over 1 factorial. This would be your coefficient, and this would be your second derivative over n factorial. So if you think about this last term, remember the coefficient is the derivative at that number over n factorial. So a to the 2 would be the second derivative over over second factorial. Okay, now let's see what's coming next. So this is radius and interval of convergence. So it says a power series in x can be viewed as a function. So here we're actually saying the function is equal to the power series. Remember, we started out saying the function is approximately equal to some degree polynomial. Now we're saying the function is actually equal to the power series. It says where the domain is the set of all x's for which the power series converges. So this says determining the domain of the power series is the primary concern of this chapter. So we're figuring out how far out we can go from the center number and still say that we converge. Remember, as you go farther out, we're getting a little bit worse. So we're saying, well, we're going to restrict the domain here. when we go ahead and use this equal. So this says, of course, every power series converges at its center, because if you let n equal 0, if you put a 0 here, this would become 1, and you would just be left with this coefficient times 1. Every other term would become 0. So you're saying at its center, it's going to converge. Or at the x value that you choose, it's going to converge. So the next theorem states that the domain of the power series can take on 3 basic forms. It can either converge at a single point, at some interval around that c value, and the single point would be your c value, or maybe everywhere. So they have some pictures here. So this would be convergence at a single point. So this converges only at the center. You can think of this as almost like a tangent line approximation. That very first picture we looked at where we had e to the x, and then we said a tangent line, it would be perfect only at that point. So that's like a tangent line approximation. An interval, or could also be called a radius of convergence, means you have your center point and then you have some interval on either side of your center point. So from your center point out, and that's a distance. So that's what we call our r. So this is an interval or a radius of convergence, and we call that distance r. This one says if r is infinity, that means it is an infinite radius of convergence. So remember, pause the video, fill in these notes if you need to. Here is the theorem for kind of what was in those pictures up above. For a power series centered at C, precisely one of the following is true. The series converges only at C. There exists a number r such that the series converges absolutely for your x value minus your center less than r, or for greater than r. So it's an interval. So for example, if your interval was from -1 to 1, then r would equal not 0, r would equal 1, and your center would be at 0. So you'll have an interval, and then r is the distance from the center to the end of the interval. And then it converges absolutely for all x values. So the number r is the radius of convergence for the power series. If the series converges only at C, the radius of convergence is 0. So for this situation up here, r is 0. If the series converges for all x values, then that would be here. So for this situation, r would equal infinity, also what I wrote in up here, or it's going to be some interval. All right, let's look at some examples, because we're already at 8 minutes on this video, and we haven't even looked at an example yet. Now, here they're just kind of qualifying this and saying, hey, we're talking about r, but we don't really know what is happening at the endpoints. So each endpoint must be tested separately. We're going to do this later in chapter 9. So for now, you just have to think when the radius of convergence is 0, we're only worrying about that point. When it's infinite, there are really no endpoints. These are the situations we could have right now. If it looks like this, if you have your parentheses here, this means it's diverging at both endpoints. This bracket on the right means it's actually converging on the right. So at that x value, the series converges. At this x value, the series diverges. This would be converges on the left, and this would be converges at both endpoints. So this example kind of helps explain how these intervals go. So it says, oh, I solved this one. I'm going to put a piece of paper over here. Let me just cover up these answers as we go through them. All right, so here's your power series. That number is what we're centered at. So we're centered at x equals 2. We don't really know anything else about it, but we know it converges at x equals 6 and diverges at x equals 8. If it can be determine, state whether the series converges and diverges at these x values. So I give you a number line here, and you should start labeling some parts of it. So the center is at 2, so that's your center. We know it converges at 6. So from 2 to 6 is our radius of convergence. For sure we know, because it always converges at the center. They're saying it converges at 6. So I just went ahead and drew in this r equals 4 in the positive direction. And then my yes here means yes, it converges here. We know it diverges at 8. So we know this radius of convergence. Well, we know it doesn't converge at 8. We kind of don't know what's happening in this area right here. And then if it converges 4 to the right, it's also going to converge 4 to the left. So if you go backwards 1, 2, 3, 4 spaces, you're at -2. You can think of that as your other endpoint. So let's check all of these numbers. -8, way over here. It diverges because it is not in the interval. -6 over here also diverges, not in the interval. -2 is an endpoint. Now remember, we don't really know what happens at the endpoint. Maybe it converges, maybe it diverges. We really can't determine that. -1 is in this interval, so it converges here. This is an endpoint. Every number in between here, it's going to converge. So -1, it converges. Also 0, 2 is the center. It for sure converges there. And 5 is within the interval, or it's less than 6. So we know it converges at all of those. 7 is kind of a maybe. We know it converges here. They really didn't tell us this R. I'm just kind of writing that in to help me figure out where I go from the right and the left. I know it diverges here, but I really, this between 6 and 7 is kind of a question mark. So that's a maybe, or cannot be determined. At 9, if it diverges at 8, it's going to diverge at 9. So at 9, it diverges. So that kind of helps with the interval of convergence. Now, okay, next part is the ratio test. I will do that in a separate video.